Right. Good morning. Welcome back, everyone. Just by way of updates and reviews here, you had a quiz on the card graph matching that was supposed to be due today, right? I think there's a handful of you that didn't do that yet. So it's still there. It's still open. We're not going to talk about it today. But if you didn't do that, you best do that before you come back on Monday. That's for a grade, so you need to do that. What I'd like to do, and if I've been emailing some of you back and forth about your GeoGebra tutorials. I posted grades. If you got 10 out of 10 and you didn't get an email from me, fantastic. Some of you are still having OneDrive issues sharing with your folder. We can talk about it. Don't sweat your grade. We'll get it in there. Not just for Math 104, I want you to understand how OneDrive works. So as you go on to your next class and your next thing, as you save your documents, as you share your documents, I can't tell you how wonderful of a tool it is. So I really want you to understand that and learn that, not just for this class, but I think it'll be in your best interest. So we'll continue to work with that. But I want to get to what we are going to do today. We're still on section 1.3. Some of you have already started on your 1.3 quiz, the math quiz. Some of you haven't even started yet, and that's okay. But today will be the second and final day that we're going to talk about 1.3. The very first thing we're going to do is we're going to do another Desmos activity. And you'll notice I posted 5 out of 5 for all of you for doing the Desmos graphing stories the other day. And I'll do the same for those of you that complete it today. So if you go to 1.3, and I'm on that course docs and links where we were yesterday when you saw the picture of my odometer and the card graph matching. Underneath there, I added 2 more things, and these are the 2 things we're going to do today. So I want you to go ahead and click on the Desmos. It's called average rate of change. And you should all be populating into my teacher dashboard. Okay. This one has a few more steps, but the steps are going to go just a little bit faster. Morning. If you go to course docs and links, I posted a new Desmos called average rate of change, and that's what we just opened. So the first one is just kind of a, practice. There's really nothing to do. So play around with the first one. And I think the second one is kind of just a play around as well. And then eventually that's going to ask you to start entering some data. So I'll let you just go through it. Step 4 is the first one that they're going to have you actually enter an answer. The first 3 are kind of like they're just giving you information and having you watch the graph. Now you can use a calculator if you want. The other thing you can do is I think you can actually type right into the bar like 10 minus 5. I'm not sure about this. 10 minus 5 divided by, I'm just making numbers up, 7 minus 2, enter. Or divide, yeah. Do you see how, like if you type math stuff into the bar serves like a calculator. So I just typed in 5 times 5 and it spit out 25. So you could actually type in the numbers, or you could just pull out your calculator if you want. Of course, now after I told you that, it didn't really spit out an answer, did it, for some of you? So maybe that was a bad idea. Sorry. Like Dalton, when you punched yours in, it's probably correct, but it didn't calculate it for you, did it? It just kind of left it as. So maybe punch it into your calculator and get a decimal. And yeah, I see a few of you did the same thing. I thought it would spit out the answer, but it's not doing the computation for us. So far I got 3 people that are agreeing, 4 people that are agreeing. Very nice on step 4. For those of you that, I know a couple of you are still going, I think 4.65 was what we wanted, right? That's just about everybody had that. Notice step 5 says to include units. So our distance is in meters, our time is in seconds. I don't even know what step 6 is talking about when it talks about physics. Are they looking for a certain term? Anyone?
I think say polynomial.
Say it again.
Yes.
What are you trying to say right now, Matthew?
Is that one that says a polyunus or whatever?
Yeah, meters and seconds.
Yeah, like why does it say polyunus?
Remember I can make it anonymous. So Elena, Jean, Michael, these are fake names. But if I want to see what everybody answered, there's Gage,
Yeah, but
Hannah.
mine might have to be a Polish.
I don't know who that is.
Benjamin.
I don't know who Apollonius.
That name.
I like Elena. I mean, my last name's cool.
Piscopia. These are real people. I think they're like mathematicians and physicists, and I haven't taken history of math in a very long time, but these are real people. So you're being assigned the name of a fancy mathematician. Yeah, so again, for those of you that are trying to enter the stuff into the... Did that work for you, or did you have to punch it in manually? You had to punch that number in.
Did it in there, and then
Did
it
it?
comes out, and I just deleted it and put it.
Oh, so I see. It is spitting out an answer on the right.
Yeah.
It's just not showing up on my screen. Ah, okay, thank you. You learn something every day. Should be able to get through this in a few more minutes. Let's see. Gage, I want you to double check your step 10. Ryan, I'd like you to double check your step 10. Hannah, I'd like you to double check your step 10. Very close, but there's a couple small mistakes going on here. First of all, we got to keep our variables correct, right? We want the y-axis, the change in y, divided by the change in x. So for y, we have gigabytes. For x, we have days. So it should be gigabytes divided by days. Therefore, our answer is gigabytes per day. I think we should have got 1 divided by 20, right? 1 divided by 20, which is 0.05, right? So Anthony, yours is your variables are backwards, right? Because you actually, so when you came up with 20, you did 20 divided by 1, whereas we should have done 1 divided by 20. You did the change in x divided by the change in y, but we want the other way. Change in y divided by the change of x. That's an easy mistake to make, but that's why we're doing this activity, right? So we should have got 0.05 gigabytes per day is what we should have got on step number 10. Landon, double check your number 11. I'm thinking you either punched something in your calculator wrong or you counted one number wrong. Yes.
I know you talked about this, but did I put these numbers in there?
So you should get, this is 1, and this is 20, and 1 divided by 20, 0.05, 1/20th is 5 hundredths, right? I think you did it, right? Let me double check yours. Which number was that one? 10. Did you even enter an answer?
No.
Oh, I don't see your name on there, that's why. Yep. There it is. Gigabytes per day. Wow, lots of different answers for number 12. All we're trying to do is find the average rate of change. So the final answer is all they're asking for. How much is it changing? So far, I only see 2 correct answers. 3 correct answers. What should we be getting for number 12? 7. What's the label on number 12? There is no label because it didn't tell us what x and f of x were, right? It's just a random graph. So what do we need to do? Well, we need to figure out if we're traveling from left to right. So I'm going to start with x equals 5 because that would be the second one, if you will, if we're going left to right. If I plug in 5 for f of x, I get 5 squared, which is 25, and 25 plus 3 is 28. So 28 is my first y value. If I plug in 2, I get 2 squared, which is 4, plus 3, which is 7. So I have 28 and 7 as my 2 heights. Well, what's the difference between 28 and 7? If I subtract them, it's a distance of 21. So my change in y is 21. What's my change in x? If I was at 2 and I traveled over to 5, I changed by 3. So I found the slope of the line that connects those 2 points. That's all we did, right? So 21 divided by 3 should have been 7. So what is our rate of change? 7. And that's it. There is no label, right? So hopefully what you found from this activity is when we drop this phrase, average rate of change, that's just another way of saying the slope of the line that connects 2 points. That's all it is, right? So remember when we brought up the graph of Jamie's odometer the other day? We didn't know what kind of squiggly mess there was in between, but we knew 2 points. We knew 0, 0, and we knew, what was it, like 63, 1920 or whatever it was. And if we connect those 2 points with a straight line, that represents the average rate of change, even though we don't know how fast Jamie was driving in between. But we know on average he was driving 25.7 miles an hour or something like that, right? So it all works the same. So notice the different ways that they gave this to you. One example, back in number 5, the answer ended up being positive because if I connect these 2 dots with a line, the slope is going up. It's increasing, right? So part of what you're going to read in your textbook for this section is they're going to give you a graph, and they're going to say, hey, where is this graph increasing and where is this graph decreasing? Well, it's really, really easy. All you got to do is look at the graph and think about moving from left to right like you read a book, or think about a car driving on the graph, and the car is driving from left to right. The car is going to be driving uphill right here, so it's obviously increasing. And then when it gets to right here at the very top, we call that a relative maximum. It's the maximum point. Right at the very top, it's not increasing or decreasing. It's flat for like a millisecond, right? So it's increasing from 0 to whatever value that is, and then it's decreasing from that value for the rest of it. Uphill, downhill, right? So that particular answer was positive because the 2 points we were looking for were on the increasing portion. But then when we go over to Mr. James' checking account, if I was driving a car on this graph, obviously I'm driving downhill, right? That's why the slope of this line was negative. So it's a negative rate of change. If I go to the cell phone one, number 10, it doesn't matter where I put the 2 dots. It's always going to be what? The slope is always going to be positive unless we have a point where we don't use any data at all. Let's say we went a day or 2 or 3 and we used no data whatsoever. Is our slope going to be positive? Is it going to be negative? What is it going to be? 0. It's going to be a flat line, and a flat line has a slope of 0. It's not positive or negative. It almost looks like it flattened out there for a second, like they went a day or 2 without using any data. Is it ever going to be negative? No. Does gigabytes ever come off your cell phone? Just the same way as an odometer never goes backwards on a car, right? So this one is always going to be positive. So they can give it to us in a graph. They can give it to us in a table. There is no graph. Could you make a graph if you wanted to? I suppose. You could plot these points. Plot, 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 and plot. Okay, and we can practice this on our GeoGebra. Now, do we know what's going on in between 0 and 1? No, but we could guess that maybe it's just a constant flow. I don't know. We'd have to look at the graph and take a stab at it, right? So here you just had to use 2 points as opposed to being able to view the graph. And then finally, they give us one that is just abstract altogether. They don't even tell us what x squared plus 3 is. We don't know what x is. We don't know what f of x is. It could be time. It could be money. It could be water. It doesn't matter. It could be anything, right? So it's just abstract. So what I'd like you to do, you can leave that open if you want, or you can close it. But if you go back to Blackboard, I want you to open up this GeoGebra where it says explore the difference quotient, average rate of change graphically with GeoGebra. I made this GeoGebra just for playing around purposes. There's not much to do other than play around. What your book is going to show you and what you're going to run into every once in a while is this idea of a difference quotient. Okay? A difference quotient is what you guys were just doing. You were finding the difference in 2 y values. That was your numerator. Then you were finding the difference in 2 x values. That was your denominator. And then you took the quotient of those 2 things, meaning numerator divided by denominator. Quotient means division, right? So this is what they call a difference quotient. So let's say I had some value x, and I had some value h. H is the distance in between my first and my second point. So if this one is x, the next one is called x plus h. It's just h more than the other one, right? So those are my two x values, x and x plus h. Notice they have a difference of h. And then if I find the value of the second point, the height of the second point, that'd be the first green line. And if I find the value of the first point, this green line, if I take the tall green line minus the short green line, the difference is going to be the difference in height between the two. Do you guys agree with that? I know it's a little bit abstract. So notice my different parts here. Let me go like this. Let's see if I can do this here. Okay. If I go to x plus h, and I plug x plus h into the function, that would be this value right here. That's my height of my first dot. Height of dot number 1. If I go to x, and I plug it into the function, okay, I would find that value. That is the height of my second dot. So this would be the long green line, long one. This would be the short green line, short one. And if I take the long one minus the short one, that's the difference, I would end up with the difference in height, right? So what is h? Well, if I have x and x plus h, and I subtract the two, the x's just go away. H is the distance in between. That's what I'm going to get if I subtract the difference between the two x's. So let me do this here. So notice what can happen. Go ahead and drag your two blue points. Do you guys have this open?
Yeah.
You can drag your two blue points and you can make them far away from each other. Notice the further away they get from each other, the bigger h gets. See that? H gets wider and wider. The closer they get to each other, h gets very, very, very small. Very small. In fact, you can make h so darn small that the 2 points almost look like they're right on top of each other. See that? Now, any of you take calculus in high school? So if I drop the word derivative, that means literally nothing to you, or limits. Okay, that's fine. This idea that we're looking at, I'm going to see if I can erase. Oh. Just going to get rid. This idea that we're looking at is actually what we call the definition of a derivative. A derivative is an instantaneous rate of change, not an average rate of change. It's instantaneous. It's not how much movement did it average between this point and this point. That's what we've been doing all day today, right? And with the odometer the other day, we had 2 points, and we drew a line between those 2 points, and we found the slope of that line, and that's the average rate of change. When you get to instantaneous rate of change, if you guys ever take a calculus course, you're taking your 2 points, and you are moving them so close together that your 2 points almost become 1 point. Almost become 1 point. Okay? If I gave you a point, if I gave you 1 point, and I told you to draw the line through that point, how many lines go through 1 point? Infinite. I mean, does the line go that way, or does it go that way, or that way? We don't know, right? You can't make a line with 1 point. Do you guys agree? How many points do you need to make a line? 2. You got to have 2. And the cool thing about calculus is that we can make 2 points using what we call limits. We can make 2 points so darn close together, like I'm talking 0.0000000000001 away from each other, so that the human eye looks like it's just 2 points. I can make them so close together that I'm literally drawing a line through 1 point, if that makes sense. So now do you see how my gap is so small that it becomes an instantaneous rate of change, like right at that millisecond, what's happening? So I just wanted to show you that so you can feel the slope of 2 points and understand what it means to have those 2 points get really, really close together. Okay? So I want to show you a couple examples from the textbook. And you can open your textbook if you want, or you can just follow along on the screen up here. I had picked out on page 20 examples 2, 3, and 4. So let me go to page 20. Examples 2, 3, and 4. Okay. Example 2 on page 20. It says, given the function g of t, find the average rate of change on the interval from 0 to 3. So if you just look at the graph, if I punch in 0, notice that the g of 0 is equal to 1. So this is my first point right here. The g of 0 is equal to 1. And if I punch in 3, if I go over to 3, it looks like it's equal to 4. So notice on that interval from 0 to 4, it was decreasing for the first part of it, and then it turned around and it started increasing. But on average, that decrease and the increase are going to kind of cancel each other out. You can already tell if I connect these with a point, is it going to be positive or negative with a line? Positive. Obviously, it's going to be positive. So on average, what's the slope of that line? Well, you can figure it out. You can either count the tick marks, or you can do a little arithmetic, or you can do whatever you want. Looks like it went up 1, 2, 3, and it went over 1, 2, 3. Up 3 over 3, 3 divided by 3, 1. So the average rate of change is 1, right? So that one's just kind of using your eyeballs. What about this one? This is very similar to the one that we just did on the Desmos, right? With the water and the water coming out of there. So let's say I wanted to do this on GeoGebra. I'm going to close this guy. Let's say I'm like, man, I'm too lazy to pull out my pencil, or I'm too lazy to pull out my calculator. I want to know the average speed for the first 6 hours. So that's from time 0 to time 6. So at 0 hours, I had already gone 10. So I'm going to open up my GeoGebra. And I'm going to plot the point 0, 10. Because I knew that at time 0, I was already at position 10. So I plot the point 0, 10. Let me find that right there. There it is. And then the other one says the first 6 hours. So where was I after 6 hours? I was at 292 miles. So I'm going to plot 6, 292. And now I need to drag my y-axis way down so I can actually see 292. Had it there. There it is. Okay, I'll stretch this guy out just to make it look nicer. So there's my 2. And it says, what is my average rate of change? Well, in the book, they're taking 292 minus 10 divided by 6 minus 0, 282 over 6. They're saying 47 miles per hour was the average that this person drove. So this is the same as my odometer example from the other day. So it should be 47. What's going to happen if I go to my computer and I connect these 2 points with a line? It'll give me the equation of the line over in my algebra window. Gives it in general form, but I don't want it in that form. I want it in slope-intercept form. Remember I showed you guys this on the first day? If I go to slope-intercept form, y equals mx plus b, y equals 47x plus 10. The 47 is the slope of the line, which is also the average rate of change between the 2 points. Same answer that GeoGebra spit out that my textbook spit out. When my textbook did it by hand, my computer did it by graphing the slope of a line. You guys see the correlation there? Let's look at one other example in the textbook here. It says, compute the average rate of change. This is just like the last one that we did on Desmos. X squared minus 1 over x on the interval 2 to 4. Again, I can plug and chug with pencil and paper and calculator like my textbook does. Or if you're more of a visual person, you're like, you know what? I wonder what x squared minus 1 over x looks like. Well, let's find out. I'm going to delete this and delete this. I'm going to graph x squared minus 1 over x. It's this goofy looking graph. Stretch this back out a little bit here.
How did you get that algebra bar on the side?
This window?
Yeah.
It should appear, but if it's not there, click on View, and then click on Algebra, and it'll pop up. You might have accidentally closed it. Does everybody have that open? I did. I'll show you how I typed that in. You got to make sure your order of operations, you got it. For those of you that are still wondering, I typed X. When I do squared on this, I use the caret. That's the shift of the 6 button. X caret 2, that's X squared. And then I did minus, I put it in parentheses, but you wouldn't have to because it knows order of operations. X squared minus 1 over X. Now this one might be hard to visualize. See how stretched out my x-axis is? I mean, you can play with your axes, but the book wants us to go from where to where? From 2 to 4. So I actually want to see 2 and 4. So I'm going to... I was still stretched out from my previous example. Okay. I want to go from 2 to 4. Okay. So, from 2 to 4, here's 2, that's some height, and here's 4, that's some height. I want the difference in those two heights, right? So I can actually plot points if I want here. If I go down to my input bar, I can go, this is a clever little trick. My x value is going to be 2. What's my y value going to be? It's going to be 2 squared minus 4 minus 1/2. It's going to be 3.5. But watch how I can do this. I can just go f of 2, and I can let the computer do the math for me. Like, let's say f of x was this brutally awful, complicated function that I don't want to do a bunch of mental math on. If I just punch in f of 2, my computer will do all that computation for me. So I'm going 2 comma f of 2, and there, it plotted the point for me, point A.
And that's because of the function.
That's because of my red function f of x. Yep. So I did 2 comma f of 2. It did the math for me on f of 2, and it got 3.5. Now I'm going to go plot another point, 4 comma f of 4, and it'll do the math for me. This time it came out to 15.75. So I got my 2 points that I'm interested in. What am I interested in? I'm interested in the average rate of change between those 2 points. And how do I find that? I find the slope of the line between those 2 points. Again, I could do it with paper and pencil, or I can just make a line. And I'll change it to slope-intercept form again. I think it's about 6.13. That's rounded. What did the book say? 49 divided by 8. Is 49 divided by 8 about 6.13? It's actually 6 and 1/8. It's 6.125, right? 6.125 or 6 and 1/8. So again, if I go to options and rounding, I can round to 3 decimal places, and sure enough, there it is, 6.125. Comments, questions? We feel okay there? Okay, so where does this kind of come into play? The last example we're going to do here is example 7 on page 23. A lot of you guys are business majors, so you might start using this lingo. Here it says application to business. It's what they call marginal cost or marginal revenue or marginal profit. So if you've taken like an economics course or an accounting course, or I don't know, these are courses I've never taken before, but it says marginal cost is typically defined as the change in total cost if the quantity of items produced increases by 1. So what they're saying is, let's say you're a company and you're producing like, I don't know, 5,000 units of whatever your company makes. How much does it cost your company to make those 5,000 units? Well, there's probably some formula and you can calculate it costs so much money to make 5,000 units. Well, then the question is, how much would it cost if I were to just make one more? That's what we call marginal cost. So like, how much is it costing me per unit at this particular point? So if I could calculate how much it costs to make 5,000, and I can calculate how much it costs to make 5,001, how much to make one more, then my marginal cost or my average cost to make one more at the 5,000 point would be whatever it comes out to be. That's what marginal cost is. So let's look at example 7. A company has determined that the total cost of producing Q items, TC stands for total cost of Q items is 2,000 plus 50 times the square root of Q. Find the marginal cost when production is currently 5,000. Let's graph this and see what it looks like. So go to your GeoGebra, type in 2,000 plus 50 times the square root of, you can't use Q though. You got to use X. GeoGebra always uses X as your independent variable. So you're going to have to type in 2,000 plus 50 square root X. I'm going to give myself a new GeoGebra. Don't save. Okay. Yep, I'll show you how to do square root. There's 2 ways to do it. Let me change my font size here. So what was it again? How many thousand? 2,000 plus 50 times. So I'm going to do times is my asterisk, which is my shift of my 8 key. There's 2 ways to do this. You can type in SQRT. See, when you do SQRT, that stands for square root. And then parentheses X. So I can do 2,000 plus 50 times SQRTX. Notice it worked for me. The other way to do it, I got to scroll down so I can see 2,000. So I got to make my graph actually fit here. There's my graph. And then I want to scroll over, because they wanted me to analyze it at 5,000, right? So I got to scroll all the way over to 5,000. Okay, so now I have a nice fitting window, right? You should get a nice fitting window like mine. The other way to do square root of X, I could have done 2,000 plus 50 X to the what power? You guys know that one? X raised to what exponent is the same as square root?
2.
Nope. That would be squared. I want square root.
10.
Half. The half power. This is the same thing. X to the 1/2 power is the same as the square root of X. Little exponential review for you guys. So I could have gone X to the 0.5 power, and notice my 2 graphs are identical. I'll just get rid of that second one so we don't have to look at it. Okay, so what's the question asking us? What's going to be the marginal cost from 5,000 to 5,001? So do you guys agree that our 2 points are going to be super duper close together? Just like I was showing you, it's almost like you're making 2 points into one. Okay? We can make 2 points into one if we use calculus. Is this calculus class? No. So we're not going to make 2 points into one. We're just going to put them 1 unit apart, because the difference between 5,000 and 5,001 is a pretty small difference. Do you guys agree? When you're talking in thousands. So what happens if I go, I can go plot the point 5,000 comma f of 5,000. That would be 1 point. And then my other point would be 5,001 comma f of 5,001. And that would be my other point. And A and B are so darn close together, it looks like they're on top of each other. What am I interested in with A and B? The line that connects A and B. The slope between those 2 points. So I can make a new line. I'm going to click on them over here. A, B. And if I look at the slope, it looks like it's 0.35. So I think we were in dollars, right? So 0.35, 35 cents. To make one more, it's going to cost me 35 cents. Now, does that mean each unit costs 35 cents all the time? No. It costs 35 cents right there. But what happens if I did it from 1,000 to 1,001? Can you guys picture the slope if I did it right here? Would it be higher or lower than 35 cents? Higher, right? What happens if I did it from 2 units to 3 units? Really high, right? So think about business and mass marketing. When Expo makes these dry erase pens, do they make 10 of them and say, all right, we're in business? No, they make 10 billion of them and put them in boxes. So notice what our blue graph is doing. As we go over to 10,000 and 12,000 and 30,000 and whatever, what's this graph going to end up doing, the blue one? It's keep going up, but slowly but surely, what's happening? It's flattening out, because the more we mass produce, typically the cheaper per pen it's going to cost, right? So there's a little business idea for you. Okay, all I want you to do is work on your 1.3 quiz that you've already been working on. When you come back on Monday, we're going to do some more fun linear type application problems that go along with this chapter. So have a good weekend. We'll see you then.
Thank you.
Come talk to me if you have OneDrive stuff, or I'll come.